So, all right, so welcome everybody. So tonight we're going to continue our discussion of multi-decode, this concept that Ted and I were playing with. This week will be a little bit more dive into kind of the technical, how would you implement this, and then a little bit of performance out the back end of that. So based on some of the questions that we had at the tail end of last week, I put together some slides that do a little bit of review of transformer from attention mask, position coding, etc. And we'll use that as kind of a foundation, and then we'll jump into the notebook. So let me see if I can start this then. I didn't do optimize for video, but that should be okay. Can you see that?
Yeah, looks good.
Okay, great. Okay, so this week then, as I mentioned, it'll be kind of around the details of implementing. We'll go through some of the transformer concepts and then through a kind of a proof of concept implementation, and then touch on performance. I think this is just a light touch, but it gives us a little bit of a flavor of what it might look like and where its strengths are and where its challenges are as well.
Okay.
Okay.
Raj, minor thing, you misspelled multi-decode on slide 2.
On slide 2, well, MultiDecode, yes, that's the alternate one.
That's the alternate one.
While we're nitpicking, do you want to go into full screen slideshow mode?
You know what? I can't navigate as well as if I do that. Is it okay this way, or?
Yeah, it's reasonably big. It's just
slideshows.
Yeah. I'll try it. We'll see. If I get frustrated by the navigation, I'll switch back. Okay, so yeah, so this is the standard transformer, the little block that comes out of the attentionals is all you need paper, and then modified by Ted to show kind of a residual stream that flows up through with the feed forward MLP on one side and the attention on the other. And during training, I wanted to contrast training versus inference or generation. So during training, you basically are doing this massively parallel generation of output probabilities. So you'll take an input sequence, you'll run it through the transformer and generate a output probability, and then there's a loss function. You know what the next token is in our actual sequence. So there's a loss function, and I think it's a likelihood, a probability, log probability loss function that feeds back and trains this network to predict the next token. When you're doing that, you essentially, during training, you would be throwing away this last prediction because we don't really know what comes next. So that's these little blocks. There's all this processing that goes up. During that time, for every one of these tokens that's coming in, and at every layer, you'll be generating keys. In the attention layer, you'll be generating keys, values, and queries. Those get stashed away. So I tried to show this a little bit different. So this is an inference. These little green blocks are the key and value that have been saved away. So these, during inference, you do not regenerate. These are what's called a KV cache. And during inference, the only kind of forward pass through all the layers of the transformer will be for the new token that you're generating, typically one token, single token at a time generation. It'll access this attention block has access to all these prior KV values, but they're just stored away. They're static at that point. And the computation, the MLPs and all that is just in this last token position, predicting the next token. And I think this would be if you were predicting 2. This is where we're going to end up with for our multi-decode, where we're actually generating 2 output probabilities in parallel. Using the KV cache, 2 instead of 1, as we saw in this one, the traditional, we instead will be generating 2 of these predictions. Okay, and the magic, the difficult part is in kind of all the bookkeeping that goes along with that. Does that make sense? Any questions so far? Probably everybody is familiar with this already. Okay, so going back, so the attention, here's the equation, right? So it's the query times the key transpose. So this is like an outer product, and then you take a softmax of that and multiply that by all the values. That's the definition of the attention block. So the first step is that for all, so this is like in pre-training, in the pre-training during inference or training during, now I guess this example is, I would call this all pre-training. We're going to generate for all of the input sequence, we'll generate the keys, the values, and the queries. And then there's this outer product. So this is where that order n squared comes from. Every key value, every query value will be multiplied by every key value, and you get this very large matrix. We then have something called a causal attention mask, which basically says that if these are keys along the bottom, this is the first query. The first query can only see the first key. The second row, the second query can only see the first two keys. And I do have labels on the axes, Ted. I apologize that this one is a rotation of the one in the paper from the first week. This is kind of the order that I originally saw it in, so that's kind of the way I think. But it's equivalent to the rotated 90 degrees mask that we saw last week. So when you multiply those two, you get this lower triangle of all the key and query products. And those, when you run them through the softmax, represent a probability of that particular location. So query one, if this had a high value, that'd be query one attending to the first position. Well, query one can only attend to key one, but say down here at query, why is that? Oh, I've got some that didn't get updated. My apologize. So this should be query 8 all the way across to all of the key positions. It can attend to all of those. There'll be usually, because of the softmax, one that attends to more, and then the values will be replaced by the attention at that location. So that's, again, is kind of where we get the order n squared. You think of it when you're trading, you got these n by n attention matrices. That's where the big memory hog is. Ted talked about KV cache in a prior meetup where we introduced the idea of chunk prefill. So instead of doing all of this at once, we can do it in pieces. And so those would be these are the chunks then that we're doing. So that's equivalent, numerically equivalent to the prior. And it basically allows us to have smaller memory footprints here when we're doing this multiplication. It's going to be the same number of multiplications, but it's a smaller in-memory instantiation. To do this, for each one of them, I wanted to point out that, let's see if I can move this. How do I move? Whoops. Move that out of the way. It's getting blocked by one of my controls here. Okay. I wanted to point out that for the first chunk rather, we generate queries for all the token positions in that first chunk. We generate keys for all the tokens in that first chunk, and behind here is the values for all the tokens in that chunk. And we create a attention mask that would look something like this. I actually think it's probably truncated down. You probably don't need this stuff out here as I'm looking at it. But anyhow, that fills up this first part. And at that time, all of the KV values have been populated. So when you go to the second chunk, these locations don't need to be, or rather these keys don't need to be regenerated. You generate a new set of queries for the next chunk. You generate a new set of keys for the next chunk, but the prior KV cache is just cached away, and those aren't regenerated. So it's kind of, this is lighter weight. This doesn't include all of the forward pass through the model that the first one did, or that this part does. Does that make sense? Any questions on chunk prefill?
Hey, this is a nice explanation, Roger. And just a quick bit of color. When you're doing your chunked prefill, when you're doing your prefill in general, okay, it's doing a lot of these computing of the queries and keys, and then computing of this multiply for all the blue parts that you're showing. So this part, when you think about the GPU and what it in the current NVIDIA architecture, you think about the GPU and all the things that it can do, this is very floating point calculation heavy. Okay, so this portion does not max out the I/O of the GPU, but it does max out the floating point matrix multiply part of the GPU.
Okay. How does that shift, Ted, when we get down into this second chunk? Same story, is it?
The second chunk is the same. So for chunk 2, you basically have a chunk tall by 2 chunk wide rectangle. And so you have 2 chunk squared sort of, things that you need to calculate. By the time you get to chunk n, it's a n chunk squared, rectangle that you're doing a whole bunch of mixture ones with. So the more chunks you have, the more expensive they go, assuming that like the all white part on the top row, that you just don't bother calculating it and you just fill it in with your zeros or your negative infinities later on. Okay. But yeah, so this is very, very compute intensive, and especially when you contrast it to generating tokens one at a time, does not use a whole lot of compute, because then it is a 1 by sequence length rectangle that you're doing the matrix multiplies.
Mm-hmm. I see. So for the query, for the tokens coming in, there's a lot more multiplies going on here per token coming in.
Yeah. So for your last chunk, you're doing n times chunk is going to be your sequence length at that point. So you're doing a chunk times sequence length rectangle, and a chunk might be like 4,000. It's not like 4, right? It's not a small number. So if it's something like in the thousands, that's 3 orders of magnitude more than a 1 by sequence. Matrix multiplies.
Okay. All right. So then classically, when we are doing generation, we would have I somehow dropped the key. There would be a key generated for this position, a query generated for that position, and you would just generate one token at a time. So there should be one of these pink boxes right there and one of these yellow boxes under there. I missed that. In multi-decode generation, you generate, so whatever our beam or branch, number of branches, beam width, whatever we want to call it, you would have that many queries, and you would have key value pairs for each of the branches that you're going to be generating in that next set of tokens. And the attention mask for that is going to be, these are independent branches, so the attention mask for that is this kind of I matrix here. So we'll see this when we get into the actual code. You'll see that pattern come out.
So hold on a second, Roger. So this is conceptual, but we don't actually have 2 physical rows when we do multi-decode.
Right. Now this is the memory footprint. This is the multiply. So there's the memory footprint and the multiply, but there's just one row of KV cache for pre each item in the mini batch.
Yeah, no, but so I just want to make sure, because what you're showing physically with the pink cues would be something closer to like the mini batch approach of
it is. This is the part that I was trying to represent by here. This is the memory footprint of the sequence. This is the sequence.
Oh, wait. Sorry. No, you're right.
This is the expanded attention matrix. This is the outer product of these branch-wide queues and branch-wide Ks.
I stand corrected. You're absolutely right. So it's a 2 by sequence length. Yeah.
Right.
Okay. because we're decoding two at a time. Sorry, thank you.
Yep. Okay, and then the other thing that we're going to do is explore multi-prompt. So the idea being that I have a context, maybe a RAG result or something like that, and I'm going to be asking multiple questions of that context simultaneously. So in this case, pre-filled with multi-prompt, I'm putting in two separate prompts. So I have my common context down here, and then in the sequence I've got prompt that's only going to apply to my branch A and a prompt that's only going to apply to my branch B. Okay, and so the attention mask gets this hole in it because the prompt A is going to follow right after the context. So this little triangle matrix, lower triangle here, is attending to all of, like PA3 attends to all of the tokens before it. That's kind of standard, right? That's this lower triangle of this whole thing. The prompt B, though, is a little bit different because prompt B wants to attend to this context, but even though it's located later in the sequence than prompt A, it does not want to attend to prompt A. They're independent questions of the same context. So if you look at the attention mask, when you do the query for PB1, the prompt B, position 1, it's going to want to attend to all of the context, the C. It won't attend to the prompt A, and it will attend to the first token of prompt B. Likewise, the next token, when you're generating this token, it'll attend to all of the context, none of prompt B, and the first two tokens of prompt B. Did I say that right? None of prompt A and first two tokens of prompt B. Does that make sense? This is different. This looks different than you would normally see a attention mask. So I wanted to make sure people had a chance to understand that and ask questions. Okay, great. Okay, so then in kind of our general form, then each cycle when we're doing generation in multi-decode with multi-prompt, we're going to have a section of the mask that represents the context that we're paying attention to. A section, in this section, the two different branches have different masks, prompt A and prompt B. And then we're going to have this diagonal pattern that will repeat as we continue to generate additional tokens. Make sense? Okay. I want to make a quick comment that I was kind of thinking of these as three different types of attention masks. The first is the context, which is just linearly filled lower triangle type of thing, perhaps chunked, whatever. And then there's the section where we're adding the prompts. We're not generating text. It's kind of like a prefill, but it's a prefill where the different branches will have a different attention patterns. And then the final generate portion of the attention mask, which shows the attention mask from the point at which it branches, and then has this repeating diagonal pattern that follows after this. So if you look at this, we're going to make this query, and this key is going to follow the first prompt. This is the first prompt. This is the second prompt. So it's going to follow the first one. So we basically just yank this attention mask row right here. That's what fills in this. And then the last one, we're going to follow prompt B. So it's going to be right after this. So we copy this attention row and drop that in there. And now we have what we need to start generating tokens following prompt A and prompt B. Does that make sense? This actually, I don't know if I missed an example. This is at the second token generation of two branches. And this is the general form. So if you understand that, the rest is going to be pretty easy.
Yeah, so to kind of reiterate, normally in standard decoding, if you look at the 6 blue squares on the left as your context, so if those are rope positions 0, 1, 2, 3, 4, 5, when you keep going to the right, you just expect to see 6, 7, 8, 9, 10, 11, whatever. In this case, we're going to have two sixes. We're going to have the one that's associated with the first prompt, and we're going to have one that's associated with the second prompt. We're going to have two sevens, and we're going to have two eights. So as the way Roger drew it, there are only 3 token long prompts. So it's a very short prompt,
Right.
very short question. But and the idea with these masks is that, so I said 6, so this would be 6, 7, 8 for the prompt. And so then the next token we generate is token 9. And the token we generate after that is token 10. But if you look at the bottom where Roger has generate, if you look at either one of those rows, what you'll see is that they have exactly 1, 0, exactly 1, 1, exactly 1, 2. They have a 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and a 10. And if you just were to sort of compress everything to the left and get rid of all the white squares that are masked out, it would look just like perfectly normal decoding. It would just be the numbers 0 through whatever, n, all in ascending order. And that's true for any row. So here we only have 2 rows, but if you're doing multi-decode 5 ways, you just have a lot more white space. But the point of this is that this is an exact calculation, because what every token can see is basically just what it normally would see in standard decoding. It's just they're spread out a little bit more. So I hope that intuition.
And especially interlaced here during the generation.
Yeah.
And just for fun, I looked at what the chunking is on recent GPU architectures. And the low-level warp level chunking is 16 by 16 or 16 by 8, or equivalently 8 by 16. And then CUDA aggregates those up to 128 by 128 or 64 by 64.
Yeah, and then your like VLLM or whatever software is going to do some multiple of that likely.
Yeah, and so if you have a upper triangular matrix that's masked off, like in your diagram, they actually have a step ahead of the floating point multiplications to test for the masking. And if they detect the masking across the entire chunk, they just disregard it.
So do they actually instantiate the full mask but optimize the multiply?
They check to see if it's masked, and if it's totally masked, they don't multiply.
Right. But you do at least instantiate the full mask. You just don't do the multiply.
I don't know. Okay. I'm sure they've squeezed out. It's such a common operation. I'm sure they've squeezed out every optimization you can think of for that, because it's upper triangular masks are very common.
Dave, that's one of the discussions that Ted and I had, is we don't know kind of what optimizations might be built in for this standard attention, lower triangle shape type of thing. And there may be CUDA kernels that we can't take advantage of because this is a little bit non-standard. But I think his perspective is, but if it's a big enough win, somebody can create an optimized kernel for something like this.
Yeah, and if you look at the PyTorch code for attention, it does all kinds of redimensioning. It's confusing as hell. I was never able to wade all the way through it. But they redimension things all over the place to change the way the multiplications are done. And then when they come out the other side, they redimension to straighten it out again. So that code is heavily optimized, kind of dimensional spaghetti, to try to squeeze as much as it can out of the GPUs.
Yeah, it's an interesting area of exploration. Okay, so if we're good, moving forward then, this, Ted, you already kind of covered this, but here this is adding kind of what the position encoding is that's added to all of the key values in queries. And as Ted mentioned, so that the first ones during this context phase are all sequential, and then the prompts in my example would follow from after the context, as we might expect. So I think Ted's covered that already. And then the keys would follow the prompts. In this case, that it would be, I'm assuming that it happens to be that both prompts are the same length, and it happens to be that our queries are following, that the prompts are expected to come after the context. In one of the examples that we'll look at, the writing in the margins, these prompts actually might follow somewhere deep embedded in the middle of the context and not at the end of the context. And I think generally, whatever that prompt is, unless there's no prompt, like a beam search, these would always follow the prompt. So, okay. Oh yeah, one more thing to mention is, so this will be more for the performance side when we go and look at the performance notebook. It looks like down in the transformer implementation, transformer library from Hugging Face, they implement a beam search, and they implement it as essentially expanding the mini batch size. So they'll clone the data. Actually, I'm not sure if they repeat it or just copy it, but there ends up being independent rows in this mini batch. And they expand it, and then at the end they select one of them, I believe it is. That's one approach. The other approach is that you could actually run each of those queries independently in a sequential run. So the expanding the mini batch is cool. That has a lower latency because you're generating all of the next tokens are all generated simultaneously. But because of the way they do it, it expands the memory footprint significantly. Running them sequentially, you don't hit the memory bottleneck, but you do have a big penalty in latency and performance because you have to run the whole model every time. Would note probably that when you're doing the beam search, I guess in either one of those, but especially in the beam search, yeah, you get the performance. Problem is, a lot of times it's easy to hit the memory limit, especially if you have a lot of long context that you want to include. And the other thing is that when you're expanding that, the mini batch, expanding the memory footprint, you're also kicking out some other paying customer that can't use that pass of the forward pass of the transformer as well. So both have disadvantages, but those are the ones when we look at performance, we believe are the two kind of standard practice. Ted, did you have any comments you wanted to add to that?
Sorry, I had to unmute. No, I think that's good background. Hopefully most of the people were here last week. And so but then the main thing we wanted to do, I think what you're about to launch into is, if you have some of this background and it sounds like maybe this is an interesting theoretical idea, does it really work? Is it really faster? And so Roger has coded up a number of different examples so you can see, it does work. It doesn't actually require us to train new LLMs, change the architecture. It doesn't require us have some super special library. We just ran this with standard Hugging Face transformers. And then even at the end, Roger does have some timing stuff to show how much faster it is than if you did sort of a naive comparison. So excited for this. So Roger, I don't know how much you want to divide between understanding the code versus just showing the examples, but we'll cover both today, hopefully.
Yeah,
right?
I think I was thinking about that question from last week too. I think what we'll do is I'll kind of introduce the API to the function that we have, the building block, and I think I'll just dive into kind of the outputs first, and then that gives us an understanding. And then if people want to get into the code more, then we can roll back and do that. So if that makes sense. So anybody to just feel free to speak up if if there's a section you want to cover. But okay, so this notebook, which Ted, we dropped this in a repository in the West Coast Machine Learning. Can you drop the URL for that into the meeting notes and or the agenda or the Slack? Okay, so bunch of includes, imports. We're using the Hugging Face, so play some games with getting logged in there. This is the function that actually implements the multi-decode. The input argument says it uses a model. It's like a generate. So it uses the model and some sort of input IDs. So this would be the part C that we were talking about. It also will accept a set of positions and a mask. And so this will be include all of the context that you're feeding in, but it also applies to, you can see up here that we've got past key values. So you can pass in a KB cache from a previous chunk, for instance, and you just add this. When you add it, the inputs in that case would be the tokens for this next chunk that you're adding. Positions and masks, this would be 1 by batch size dimension. So positions would be for all of the tokens that you're adding. But mask, so these two are based on those will be kind of the same length. Mask, though, this is and not to be confused, because there's a 2D mask that some models use in the same position on Hugging Face that is masking to skip over padding tokens. We're using a 4D mask, which is, let's see, batch head, query size, and key size. So this mask has to be big enough to include not only these tokens that you put in, but also the past key value tokens. So just a little, if you go to use it, just to beware. Gen length is just how many tokens generate each time you call this. Number of branches is how many parallel branches we're going to be generating. I guess technically that could probably change every time you make a call into this, but in all the cases I've done, the number of branches that you're running is the same. Greedy, it has a little quick implementation of next token selection. So your greedy implementation, you just set that greedy false. I did greedy, I think, most of the time, but you can sample. Branch locations, I mentioned that one of the use cases that we wanted to cover was when we had branches that continued not from like the very end. Don't want to assume that it's at the very end. I want to be able to arbitrarily say where in that sequence do I start branching from. And it's actually anywhere in the full key value, past key value sequence. I followed kind of the Hugging Face model and returned a dictionary of values, which would be the branch IDs of the ones that are, this is like a deconvolved set of branch IDs. Output IDs is the mixed up set of token IDs. And the mask, more for diagnostics, is the attention mask that has all of the generated tokens built into it, and likewise positions included in that. I guess mask is more than just diagnostic, because you need mask. You need to build on mask for the next call to this if you're doing it multiple calls. Okay, and with that, I'm not going to go into, I think, the code, other than to say perhaps this is the Hugging Face interface that we're using, where we specify the input IDs, the position IDs, the attention mask, past key value, use cache. That's the standard. Not all transformer language models will support the 4D attention mask. So you have to be a little bit careful with that, but it is a standard that I didn't go through and find all that did. I'm using, I think it was Llama, which does, so that was sufficient. Okay, does that seem like enough for the code dive at this point? Okay. Some utilities for printing stuff out. Here we get started. We just, the llama 3.21b, initialize the tokenizer and the model, tokenize. So here I'm generating tokens from once upon a time. I'm creating a mask. In this case, LUT is a utility I have here to create a lower triangle with all the right dimensionality on it. Printing out the arguments, generating an output, making that call. In this case, we're going to do 5 branches and print the results. So what does it look like? These are the arguments going in. So the input is batch size of 1. I should mention that I believe this code assumes batch size of 1. It's just a simple implementation. So it retains the dimension location, which is assumed to always be 1. So batch size of 1, and the input sequence is 5 tokens. So once upon a time becomes 5 tokens. There's a little special one in front, I think, and the rest of the ones are just 1 word per token, I believe. The attention mask, you can see. So Jerry, you'd asked last time. So this is going to be the equivalent of 1 in the attention mask, and the little dots are going to be the zeros. So like in our slide, right? This is the lower triangle. All ones in the lower side, zeros in the top. When we do the generation, the raw sequence of tokens is gobbledygook. And you can see things like, the commas repeated 5 times. Out of the next 5 tokens, 4 of them are theirs and then 1 isn't, etc. So when we go back and we decode that, the little triangle matrix, the attention mask basically that we had, in this case, there is no prompt. I'm just continuing it. So it's going to be context followed by the little diagonals. We can see that I reformatted it and I included the input IDs. So we have once upon a time, everybody put in commas. That always follows once upon a time, apparently. And then you can see the there, I, there, which matches up to there, I, there. And then the next one was, 5 was's and us, 5 us. So these are the 5 sequences that we generated. Now, we generated these with only, how many did we generate? 10, was it? With 10 calls of the model. So there's 50 tokens that we generated, but we did it in 5 forward passes of the model. We can see also it returns a position that is the first 5. This is the C part, the context part that I talked about. Those are numerically incrementing, as you would kind of expect. And then these next ones are the first token of the continuation. So all of the commas are tagged with a position, sequence position of 5. The rope position is 5. And then that repeats. Basically, the way it's in a simple implementation, every time we're generating 5, every time we will get 5 more tokens. And all of them will have the same number at this point, at least. Now, they could have different ones, and I think we'll see different later, where they didn't start. These all started after Once Upon a Time, so that's why they all start with 5. Later on, I think in writing the margins, we'll see that they don't all start in 5, but there's this stanza of number of branches repeated. The attention mask, this is kind of like what I showed in the slide deck before. It has the block here. It's hard to highlight this, but this area is the block, which was the mask of the context. And then these diagonals are the ones I showed that refer to the tokens that belong to each of the individual blocks. So you can see that this token can see kind of every 5th token back until it gets to the context. Same here. It can see its tokens that were generated previously, but can't see any of the other branches tokens. Okay, does that make sense? Any questions at that point? Okay. Let's see. I'm going to skip. I'm not sure why I had select branch up there. Okay, I slid our select up to the top. That wasn't supposed to be. So here's a multi-question. So in this one, this is like writing in the excuse me. This is the idea of one question, one context, and multiple questions asked about that context. And what we're going to see is we can answer those in one, not one forward pass, but we'll be answering both of them simultaneously on each forward pass. So what I do is create the IDs, the tokens for the context. Then for each of the questions, these would be, I called them prompts in the other part in the slide deck. We get those sequences so we know what they are, get the shapes of them, that helps us reconstruct it. So the input IDs is going to be all of the context plus both of the questions or prompts. We concatenate those, and that's now the sequence that we're going to do our prefill on. In this case, we're going to build a special mask. So I start with a lower triangle for everything, and then I zero out the part so that question 2 cannot see question 1. Then positions, we go 1 through n, the length of the context plus the question, and then we do the second one starts at the context length plus the length of question 2. So this is should be the position after. Yeah, okay. So here we got the position vector showing it's a long context. This is prompt 1, and then this is prompt 2 that came out of it. So you can see, as Ted had mentioned earlier, like 17 occurs twice in this sequence, 1 for each of the prompts. Because the prompts both are supposed to follow the context. It's a longer context. That's why this is a longer context. That's why we're way out at 16 before we do that. Okay. The attention mask, this looks like that slide I had before with the context probably to about here, and then prompt 1 and prompt 2, question 1, question 2. Okay, so okay, the bike is purple. Okay, what color is the bike? The answer is purple. This one again is the same thing where they're all mixed up, interleaved. This is reformatted on the output. So this is the context coming in. What color is the bike? The answer is purple. What color is the grass? The answer is green. So those two questions were answered simultaneously with whatever it is, however many tokens that is of the forward pass. So two beams, two branches rather, answering their respective question, what color is the grass, what color is the bike, answering simultaneously. Here's the attention mask that we got. Remember I said it was like copying the mask. So one of them would have copied this one, and then the other would have copied this one, and then interlaced their little diagonals across the end of it. Does that make sense? Fortunately, I think I happen to get questions that are the same length. So I think this also starts at 17. They both of these start at 17, so we don't get to see that. Okay, so that was simultaneously answering independent questions. The next one was motivated by our idea. Well, let me stop there, pause there. Any questions so far? Have I lost everybody, or is this just obvious? Okay. Jerry's
Good.
laughing. I think that means I've lost. Okay, so writing in the margins then. This one will be a little bit different. So in this case, we want the questions not to be answered from the end of the contents. We're not asking simultaneous questions of the same context. Instead, we're asking the same question, but we're asking it to reference to different parts of the same context. So in order to be able to keep track of where those parts were, I created context 1 and context 2 so that I can know kind of their lengths. I concatenate them when I'm building the input IDs. I also concatenate the question, the two questions. What color is the bike? What color is the bike? It's the same question. At first, we were kind of thinking you could use that, just reuse the question, but you can't, because the prior history of each of these questions is going to be different. One time the question is asked in the middle of the sentence or the context, and the other case it's asked at the end of the context. So you actually have to have the question repeated. Ted has some crazy idea on how to essentially shorten the question that's different. Ask the common part someplace with some sort of trigger word, and then you only need to see the trigger word later in the context. But you would have to have each trigger word would be repeated once for each branch.
Yeah, so if you had a really long question, given this assumptions and this and that, I want you to answer the question, boom, 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 boom. So then later, what you can say is, later on, when you see the word answer, or when you see this special symbol, or when you see answer in triple quotes, or whatever, right? Answer in square brackets, something like that. Please answer the question I just told you. That's really long. And then later on, towards the end, you can just have the word answer for each thing that you want it to answer the question about. You always need to have at least one token worth of unique prompt question tokens for every chunk of data that you want to process in parallel. But there's no need if you have a long question that's 300 tokens. You don't have to repeat the 300 tokens every time, as long as you can do something to tell it what the common question is. And then when you see the word answer, then answer this big long 300 token question.
Okay. All right. So in this case now, then we again start with a lower triangle, but we're going to mark out different stuff. So question 1, we don't want to see the grass was green, the bike was blue. We just wanted to see the house is red. So we got to zero out that. And in question 2, we don't want it to see question 1. It's going to see all of the context, both these context 1 and context 2, but we don't want it to see question 1. And so that's what this magic does here. Likewise, we build up the positions so that they're sequential. Both of the questions follow the context. Well, both of the questions follow the part of the context that they're allowed to see and not see the other question. So this will be more clear when we look at the output. And likewise with the position, same thing. Okay, so the input to this then, the input to this, this would be, let's see, what is this? Probably, this is all of the context prompt. This is 7, so this would be question 1 that's going to follow token 6. It'll start from there. And then it looks like probably here is position 19, which follows the last position of the full context. So again, bookkeeping to keep track of the right positions, but everything, if you look at the information associated with each branch, they all would just look like sequential positions and skips over things you're not supposed to see, like somebody else's question, or in this case, the rest of the context that we're not allowed to see. So the matrix now, the attention matrix looks something like this then. So down to here is going to be all the long context. It's, all those tokens can see the tokens that came before them. this would be the beginning of question. The first time they ask the question, we're asking it to only pay attention to the first part of the context, the first, what do we say? Well, the house was red. That's all it gets to see. That goes down down to here. So that's the question. First time you ask what color is the bike. The second time you ask what color is the bike, we're now allowed to see all of the context, both the color of the bike, the color of the grass, the color of the house. But we don't want to see the question one that we've already asked. And so that's why this is zeroed out. So the result that we get out of this is unsorted there, but here, this is including the part of the context and the prompt, the question that it can see has been restructured here. So we see the house was red. That was a part of the context it could see. And we asked what color of the bike is the bike. And the continuation, the text generated is the house was red to what color. So it didn't know. If you had a way to measure, did you answer the question, what color is the bike? That didn't answer what color is the bike. And the reason it didn't answer it is it can only see the first part, which is the house was red. So if I told you the house is red, what color is the bike? You're like, what? I don't know. And so that's why this doesn't make much sense as you look at it. Now, the second time we asked it, we've got the context, the house was red, the grass was green, the bike was blue. The second time we asked the question, what color is the bike? And the text generated, the answer is blue, which is what we expected. So this, to us, kind of demonstrated that this idea of using multi-decode to do writing in the margin style simultaneous generation of responses to writing in margin type of questions seems to work. It's a demonstration that it works. The positions, I don't know if I want to go through in here exactly. The one thing I'd say is that this guy, all right, sorry about that. The one thing I'd say is that here, so this was the prompt that followed this part. And this was the prompt that followed the end of the context. And when we got into the generation, this token followed the end of, where was prompt one?
I think the main thing is if you go to the very end of generation and you just look at the 23 and the 25.
Yeah, that's the easiest way to see it.
You can see that the tokens that were generated did not have to have the same rope number just because you were doing parallel generation in multi-decode.
Yeah. Yep.
So, So there's a lot of bookkeeping. So you can thank Roger for writing the code, doing all the bookkeeping, so you don't have to do the bookkeeping in your head. But the key idea here is in this case, right? So first, Roger showed you an example with what was it? One piece of data and two questions. And in this case, now we have two different pieces of data. And so this would simulate the writing in the margins, the brag type of situation where you go to your vector database, you bring back multiple documents, but you want to ask the same question, what color is the bike, of each document. And some documents will be good, vector database hits, and you'll actually get data back. And other times you won't. So in the writing in the margins paper, they actually take the little snippets that come from asking the question. So in this case, you can see that first row, the 0th generation said the house was red at the beginning of its answer. And so then they just have a classifier that says, does the string, the house is red, have any useful information for the question, what color is the bike? And it would say false. And so they would actually throw that one away. And then they would say, the next one you see, the answer is, blue, right? And so then it's like, is there any information there? And it's like, yes. This does help answer the question, what color is the bike? And so it would keep those. And so these are the little cheat sheet, what they called in the paper, like the margin notes you might write on the edge of a book, which they use to improve accuracy of RAG question answering. So there's a whole bunch of references here back to writing in margins and RAG. But the key thing here is we wanted to show you examples where you can have single context, multiple prompts, and you can also have multiple contexts, single prompt, or multiple prompts is also an option. So, but there are different use cases, and the idea of multi-decode generalizes to really any of a number of very different use cases. The main thing is if you just do your bookkeeping so that your rope embeddings and your masks are set up right, any one given token that's at position 23 has the ability to see a 22, a 21, a 20, all the way down to 0. And all the positions to its left, the 22, it sees the correct subset, and the 21 sees the correct subset, and the 20 sees the correct subset. So to all of them, this is identical to just a regular, ordinary linear sequence. But what we're taking advantage of is the ability to have custom masks and things. And when we were talking about, David, I think, was saying that, the NVIDIA GPU at the lowest level of hardware can do 16 by 16 matrix multiply warps. If you're doing a 1 by 16, because you're just doing standard decoding, you're sort of wasting some of that hardware. They might have like a special thing where they can do things that are smaller than 16 by 16, okay? But there's a highly optimized 16 by 16 that doesn't cost you that much more than a 1 by 16. So if we said we're going to do 2 questions, 3 questions, 5 questions, 8 questions, up to 16 questions at a time, all we're doing is taking an inefficient 1 by 16 matrix multiply that's happening in your GPU and turning it into a 2 by 16 or a 8 by 16 up to a 16 by 16. And it's really not costing you anything more at the GPU level to do these. So at some point, yes, I think, Roger, you had some experiments that were 128 simultaneous generations. You're going to see some change to the speed, to the numbers, but it's a relatively small cost for what's 2 orders of magnitude faster data generation. So hopefully that message gets across, even if, again, we're trying to show you the bookkeeping to show you that we really did do this. We didn't cheat. But if this gets implemented by OpenAI, implemented by VLLM, you don't have to keep track of any of this bookkeeping. It'll just be done in the software automatically.
One other thing I was going to mention, Ted, is so we have right now in this example, we have kind of the core engine of if you've got the position, if you've got the attention mask, and branch locations and input IDs, they're all using the same MD-Gen. The bookkeeping right now is all done by hand. This is a nightmare, right? So like the next step would be a use case that says I want to do multi-question and answer, where I just say, tell it, and this was the right in the margin. I say, here's my context, here's the places I want you to ask the question, here's the question I want to ask, give me a mask and position matrix that works for that. And then if I do something else, if I want to ask concurrent questions of the full context, here's how I do it. So have wrappers around something like this engine, but all of them use the same. The multi-decode is all really down in here. I'm going to go backwards before I get into Ted's examples, because I think these are...
Hey, Roger, just checking the time. Yeah. So I don't know if we have time for that, if we want to just show some of the speed curves first.
Let me zoom through zoom through these then. I won't go through the in great detail, but just show. So this is the one where if you're doing a beam search, you do a beam search for a while, then you want to commit to something. So in this example, we had a context, we did a beam search and got these three answers, three beams. This little function somewhere, select branch. Select branch will update the KV cache by truncating it and then adding a new set of positions and masks. So the example of how it works is we select once upon a time was the first prompt. We got these. We select, I think it was number 2, generate a new attention mask based on that. And then the results would be, so this should have been once upon a time, a small nation started a revolution for the independence. They all start with that, but they continue in their own direction from there. And what we've done is we compressed. Before we had a whole bunch of dots, empty spots in our attention mask. We've compressed that down now, and we've committed to the first part of the prompt. So this is, you kind of recursively, I think in a beam search type of thing you would, or entropics type of thing, you would explore a few options, the multi-branch reasoning. You'd explore some options and then you'd commit to a subset of those branches. Consolidate this down so that you're not wasting that extra space, and then continue on. So that was just a demonstration that worked. This was Ted's example. I won't go a lot of time here, but Ted's example of it really doesn't matter what location a token is in. It just matters what its rope encoding is and what the attention mask is. So I did a simple one here with just 5 minus 3 equals, and we got the prompt, the answer 2 back. Part 2, we scrambled it. And so the actual question that we got is 5 equals minus 3. And the answer, as you might guess, is 2, because all of the mask is not your lower triangle. It's warped in a way that allows everybody to see the tokens they would have seen before warping. And the positions are not sequential. They're also, positions are not sequential. They're also permuted. So anyhow, that was just an example of Ted's code, or Ted's idea for Ted's example in a slide. Okay. If we don't have questions there, so this is the second notebook. And I've gone through and kind of simplified it, but it happens to be, this was the first notebook we were exploring MDecode. So I'm using a different implementation. In this one, we had a different steering function that was exploring the idea of providing a steering function to the multi-decode. So it's a little different from that perspective. But again, implement the model. In this case, we have this steering function, and then we do the the multi-decode. Again, once upon a time, and there was, so the 2, this one handles more than one in the mini branch. So here, just to prove that it's working, this is example of 2 different contexts and 10 different responses to each of them. And you look at them, you kind of start to get a feel for, yeah, that looks right. When you get things like positions or stuff like the mask off, it's interesting how these questions, the answers, the model just doesn't get it, and you can kind of pick up on it. It's like, oh, this one thought it was supposed to have a word that followed time or something like that. But anyhow, that's just demonstration of that. Here's the naive implementation. This is the one that did the repeat interleaved. So this is the one like you would do, like Hugging Face Beam Search does. I use sweepers to do it. Let me just get on down. So I ran through it. I'll just print the database, data frames out first, and then we'll plot them. But this is a way to sweep that goes through and populates all this varying context length. The 3 kind of knobs we can turn are the length of the context that precedes the generation, the number of branches that we're exploring and how many tokens we actually generate. MDecode is the time averaged over a few runs to use the MDecode algorithm. SEQ is the time if we were to process them sequentially, and MB is the mini batch, expanding the mini batch to accommodate all of the branches. And these are the execution times in this big frame. Under those three columns are the execution time averaged over some number of runs. So in this example, I just ran through these combinations here. So context 0 with one branch, 2 generated, one branch, 20 generated, 10 branches, 2 generated, 10 branches, 20 generated, and then one with a long context, 10 branches, 10 generated total. I should say that
Roger.
Yeah.
The speed up column.
Go ahead.
When it says 0.9, that's just essentially saying it didn't speed up. Is that what I'm? Is
Right.
that
It's a
how
little
I
slower. Yep.
Yeah,
Yep.
and then the other one that says 9.386. You were 9x, a little bit better than 9x.
Yes. Yeah.
Okay.
Yeah. It's just basically what would it be? This number divided by this number is
Got
the
it.
speed up. Yeah.
Okay.
And likewise,
And where
here-
you see it's slower, it's because num branches was 1, so it wasn't actually multi. So Roger's doing all this extra bookkeeping, and we're still only generating 1 token at a time. So that's why it loses.
Oh, okay, that makes sense. So I see.
So I should mention one thing. Initially, I did this naively, and so when I did sequential, I actually ran the generation n times, where n is the number of branches, and then timed that. In here, that was taking a long time. I optimize it to where I do one branch and multiply the one branch generation time, or not branch. Yeah, I guess I'd call it branch. One branch, multiply it times the number of generations, and that's how you get the. Excuse me. Here we go. I run one branch and then multiply it times the number of branches to get the time for sequential. MB, the mini batch, you can't do that. You can't. I didn't assume that anything about the nature of the mini batch, so I run that completely. But the sequential, I optimized. Anyhow, yeah. So the speed up. You can see when you start getting out with more branches, you get higher numbers. Certainly for sequential, compared to sequential, they're big numbers. When you're doing speed up against the mini batch, they're about in the same neighborhood. When you start getting up there with a large context, then it starts getting the gain is quite a bit higher. Here I was exploring. Given a fixed context and just 2 tokens generated, I wanted to explore more branches. And you can see this is one thing of note here. These are basically the GPU ran out of memory. So the mini batch grew too large and I couldn't actually do it. I should mention that I'm running on an A100. So that's an 80 gigabyte machine, right? And I'm running a, what was it, 1.7 gigabyte or something like that model, 1B model. It's not that big of a model, and we blew away an A100. So this draws the point that Ted was making, is that that use case, if you're doing very many beams, just doesn't work. It really.
So
puts
you
on
would have been
memory pressure.
forced to do them sequentially, but we know that
Right.
sequential is obviously slow because you're just repeatedly calling the LLM over and over again. That's never going to be a fast way to get results.
Yeah, you could do some sort of blend where you'd say, okay, up to this many, the memory exhaustion limit, I run them in mini batch and then run sequential mini batches.
Sorry, I didn't mean
Again,
every single one has to be, but you have to do some amount of sequential.
Yep.
But the interesting thing, I think, is even before you run out of GPU memory and would have to resort to do anything sequentially, notice that, what is that, row 7 or whatever, where we did 20-way branching, and compared to doing a mini batch where you do all of them in parallel, which initially seems like that ought to be very fast because you just have 20, batch size equals 20, and you just do all your completions and you do the same number of inference steps that we do with multi-decode. So the question is, why is multi-decode 15 times faster, even though they do the exact same number of inference steps? The reason is because multi-decode is a batch size of 1, and the mini batch has 20 copies of the KV cache, of the context. So even though it's doing few steps, each step is creating memory pressure to load that KV cache into the floating point cores of the GPU. And so 1,000 contexts is not even really that big.
Yeah.
I think there are probably system prompts that might be longer than 1,000 tokens. Like the Claude system prompt, I think is quite.
And you'd hit this memory limit earlier if you did that, as soon as I got bigger.
Yes.
So go ahead. Sorry, Tim.
So it's important to understand saving on the number of inference steps is a good thing. But before, when Roger was showing the prefill, that is compute bound. Okay. The matrix multiplies. You can get your GPU utilization close to 100% in terms of the cores doing matrix multiplies. When you're doing decoding, your GPU is nowhere near 100% utilized. And in fact, what happens is it's IO bound, constantly loading all of your tokens, which it's faster if you load the KV cache versus your raw tokens because you're saving on matrix multiplies. But even still, even when they're pre-computed, that generates so much IO that it's bringing your GPU to its knees. And then you can see clearly here where a batch size of 20 versus a batch size of 1, doing the exact same number of inference steps with the exact same model, it's getting crushed just because of that IO pressure from the extra 19 batches.
So,
and then you have a visual form of this, right, Roger?
Down below we'll get to
line chart.
Yeah. So it's interesting when you have just one branch, the decode, the sequential, and the mini batch all have very similar numbers. But look at this, the variation between 1 and 100, the decode time is so small. It changes very little from one branch to 100 branches. And that contrasts very differently than sequential, which increases by a factor of 100, or we don't get up to 100, but even up to 20, you went from, what is that, like a factor of 10, getting up to 20 branches here in the mini batch expansion. So that tells you a lot of kind of how it's what it's working here. I held the context and number of branches the same, and I wanted to explore how does this work as you have longer and longer generations, because we know the kind of intuition insight is that we're only using one row in the mini batch, but it's growing num branch faster than the other rows. So it's going to slow down a little bit, and we did see kind of the speed up gain decrease. In this example with 1,032 branches, mini batch couldn't compete. It couldn't even do it. So I run an example, I think later on, where I decreased the context and the number of branches just so we could benchmark it against mini batch. So here's the number. So this is the multi-decode execution time versus number of branches, and the scale here is just 0.18 to 0.19 basically. So this is basically flat from 1 to 100 branches. That's the cool part that we like. If you contrast it with the other two algorithms, it's the execution time of sequential is going to be huge because that's just a linear. It's 100 times slower if I have 100 branches. The mini batch isn't quite as bad, but again, I zeroed it out when I ran out, when I couldn't compute it, when I hit a memory limit. So it goes along okay, and then in this case, at 20, it died. So that was 20, whatever it is, 1,032 branches. It got up to 20, and the A100 died. The speed up ratios go up again up to 100 for the sequential, up to like 18 or something like that at 20. I don't know exactly how averaging that out, does it continue on something like that? I don't know, but it's substantially faster anyhow. Okay, so in this example, I wanted to explore what happens as my generation count increases. So this is 100 passes or 200 passes, forward passes, 200 tokens generated, 200 times the batch size generated on each pass, and compare the different approaches. So we can see this grows linear like we thought. This one actually, in this example, is 0 because it couldn't run. And the blue line is our time. And you can see a little bit of a curve in that. You can see it growing, which is kind of what we expected. It's flatter than sequential, but it's growing. So I went through and ran it again with a fewer number of branches and a shorter context, did the same thing. So we could see here. And now you can see the mini batch versus the multi-decode with a short context and a small number of branches. There is a crossover point where we're kind of curving up, whereas the mini branch or mini batch is kind of growing. I think it's going to be linear. It's going to kind of grow linearly as that. No, it might slow down also. No, it's going to slow down. It just doesn't slow down as quickly as we slow down.
So what this? Sorry, Roger. Please finish, and then I'll.
No.
Add some thought. So what this is saying is that when you are generating a lot of tokens relative to your context, then you're growing the sequence length significantly. Okay, and that's where multi-decode, because long sequence lengths we know, right, for tensions, this is not a good thing, right? Long sequence lengths are more expensive. So that is not the best use case. And so I think last week I said, generate me a 5,000 word poem is not a great idea to use multi-code to parallelize. So you would be better off just using mini batch or something and just saying do multiple of those. Okay.
Except for the memory footprint.
Well, what I'm saying is that having like 3 5,000 length mini batches, in the end might be better than having one 15,000 length multi-decode. Okay. So the use cases that really stand out would be things like RAG, things where you tend to have long context and you tend to have short answers. Then this is the screamingly powerful use case, because earlier what you saw was, 100-way multi-decode is kind of ridiculous. I don't know if anyone's going to ever actually do that, but the inference cost was flat. So if you're just generating a few tokens, heaven forbid, if you're just generating yeses and nos, which is just one token for each question, right? The cost for answering 100 questions was within whatever, milliseconds, identical to the cost for answering one, which is just crazy how well that scales for width.
Ted, were you done?
Yes.
Yeah. So I wanted to make that point again, though. It is true that when you're out here generating 200 or 1,000, that you're actually running slower than the mini batch. But you're also going to be, depending on how many branches you might be 10 or 30 times smaller memory footprint. So it's slower, but there's going to be cases where you can't fit a mini batch into this GPU. You would have to break it out do it sequentially. So it's the performance speed of inference is one thing. The ability to fit it in is another separate thing.
Yeah. What I was pointing to, sorry guys, we're like having this like live, like conversation, is that when you have very little context and all you have is generation, like write me a poem,
Yes.
okay, then what happens is the part that multiplies in the new batch is your context,
Right.
not your generation. So if you had literally zero context, no system prompt, no nothing, and you said in as few words as possible, write me a super long poem, okay, then the write me a super long poem is the only part that's repeated when you do mini batch.
Yep.
And so in fact, the multi-decode will have as much memory pressure because while the mini batch is let's say we're doing 5 of them, is five times batch wise wider, our sequence length is going to be 5 times longer, and the KV caches will actually both have the same number. It's just one of them will be really long and skinny, and the other one will be 5 times shorter and fatter, but they're going to have the same IO pressure.
Yeah.
And so we don't win in that extreme case. So I think that's a very, very extremely unlikely use case that you would think about parallelizing extra long generations with absolutely no context. And in this case, not even a system prompt, basically, because that's what Roger had to do to make multi-decode look worse.
Yep.
Was this pathological case. Cool.
I think that is it.
Nice.
Nice job, guys.
Yeah, really, really interesting.
So, ultimately, I think this presentation would be even more convincing if we said, and we just implemented this, and we ran the standard RAG benchmarks or whatever, right? So we're not quite there yet. What we didn't want to do is we didn't want to sit on the idea and wait the extra how long it would take us to run these benchmarks or whatever. What would for us be more exciting would be to get the word out and have somebody who's doing a bunch of RAG to say, hey, you know what? I'm already doing RAG. I'm set up to run some of these benchmarks. Let me now just flip to some of that multi-decode code and run my exact same benchmarks and see how much faster multi-decode runs. Or if somebody else, I heard an example, I don't think I mentioned this last week, a company had customer support calls, and they had a very large number of transcripts of customer support calls. And what they wanted to do was flag calls for certain kinds of review, for the manager to review, for them to talk to the employee, whatever. And so they had a list of questions, like, did the customer get angry? Did this happen? Did the agent do this? What was the tone? Blah, 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 blah. I don't, And so you can easily see how this is the kind of use case someone might do. But so this is the embarrassingly parallel use case where they had, let's say, a dozen questions. They wanted to ask all dozen questions on all tens of thousands of transcripts. And so what they ended up doing was 12 times n inferences. They did relatively efficient inferences. They cached the KV cache for each of the calls. So they were smart, but even still, they didn't know that instead of doing 12 times n inferences, they could have just done n inferences and answered all 12 questions simultaneously for each of these tech support calls. And in particular, from my understanding of this use case, the questions were yes/no questions. They were not long generation questions. It was, did the customer get angry? And if the answer is yes, then that's likely one of the ones they pull out for review, right? And did this happen? And did that happen? And at any point, did the agent use a word they shouldn't have used, however they worded it? You know what I mean? So these are mostly yes/no questions where the yes means something bad happened. And so this is like the ridiculous perfect case. So if you're analyzing a batch of text, um, then multi-decode is so much going to be your friend. And you can get, for one word answers, you basically will be able to do linear speed up. So instead of doing 12 times the number of passes, you will do 1 times the number of passes. And those 1 times passes will not be more expensive. They won't be 12 times slower or 2 times slower or anything. They will be like a fraction of 1% slower. So essentially full linear speed up, which is just, pretty insane. Once you start doing multi-decode as a standard thing, because especially like we were talking about, the NVIDIA GPUs can probably do up to 16-way matrix multiplies super, super, super efficiently. My guess is that if you are the actual vendor like OpenAI with ChatGPT, you can basically serve answering 2 questions at once with roughly the same GPU cost as if you were serving just 1 question at a time. And so you can change your pricing and your user interface to incentivize people to set up the way they use your LLM in a way that's, GPU efficient. So that opens up the possibility that just like that batch question answering, thing, if they could have a standard API for batch multi-questions, that's way, way cheaper per token than the not batch, just serial, do it the dumb.
Very cool.